Hello everyone, my name is Amara. I'm here today with my co-presenter Jessica, and we're from the Apple compiler team. Welcome to our talk, Bringing Up GlobalISel for Optimized AArch64 Codegen. Let's get started. This talk assumes some basic knowledge about what GlobalISel is and its purpose. If you want to know more details about the GRSL origin story, you can find them in previous developer meeting talks. Having said that, let's have a quick recap for those who are completely new to the project. So, GlobalISel is a new instruction selection framework designed to replace FastISel and SelectionDAG. The biggest difference between GlobalISel and these other frameworks is that GlobalISel can process the entire function at once, whereas SelectionDAG has to process individual basic blocks. There are some other key design goals as well. Namely, we designed GlobalISel to be very customizable so that targets can adapt it easily for their specific needs. And also, we designed it to be fast in compile time as well. Now, for the AArch64 specific implementation of GlobalISel, well, we've been working on it for a few years, and back in 2018, we enabled it for row 0. And since then, attention has shifted into the next big milestone, which is enabling it for all optimization levels. Enabling at optimization levels is a much more difficult job than O0, namely because the IR input to code generation is much more diverse when you have optimizations enabled. And of course, SelectionDAG is a highly optimizing framework as well. We have a high bar to meet there, and when you're running with optimizations, small differences in runtime performance or code size really do matter. So we did a ton of work in order to catch up to SelectionDAG, and we're almost there. We'll cut to the chase and present our performance data first. First of all, let's define what these performance metrics are. We have three main things that we're measuring. First is runtime performance, and we measure this on Apple iOS devices. And these benchmarks are some of the standard industry ones. So we have Spec, 2006, 2017, Geekbench, the LLVM test suite, as well as some internal benchmarks. The second thing we're measuring is code size. And for this, we measure code size at the -OS and -OZ optimization levels. And the actual test suite we use is the CTMark subset of the test suite, as well as some internal projects too. And finally, the last metric that we care about is compile time, and compile time is measured at OS and O3. So let's look at runtime performance. This graph here shows our relative improvement versus LLVM 10, which is a few years ago now. When LLVM 10 branched, the GlobalISel implementation had basically no optimizations really. So this is showing our geomean regression to SelectionDAG. As you can see on spec int and spec fp to 2006, we are roughly 6 to 7, 8% slower geomean. And within that number, of course, some benchmarks were significantly worse as well. Right now, we've brought that geomean regression on trunk down to less than 1%, and the actual performance number varies from run to run as well, but we're almost there. Now let's look at code size. Again, comparing to LLVM 10, we initially started off with a very large regression, a geomean of 9 to 10% on both OS and OZ. And we've brought those numbers down again to less than 1% at 0.6% geomean regression each. And we have work to do here still. Now let's look at runtime performance in a little more detail. This chart is showing the performance versus SelectionDAG on Geekbench single-threaded. As you can see, most of the sub-benchmarks are showing within roughly 1 to 2%. However, we do have 1 or 2 outliers here with larger regressions than that. On the other hand, we do have 1 or 2 performance improvements as well. So the picture is mixed, and we plan to address the regressions in the near future. On Spec 2017, we also have some runtime regressions as well. However, we haven't spent any effort yet in actually understanding what's going on in Spec 2017, since we've recently started running it. Now let's look at compile time. This chart shows our compile time on CTMark-OS versus SelectionDAG. And as you can see, the overall picture is that on average, using GlobalISel improves compile time by 6.1%. However, this is measuring the entire compilation, which includes the front end, mid end, and back end as well. What happens if we isolate the actual instruction selection part? Well, if we do that, we can have a more apples to apples comparison. And we time all of the combiners, the legalizers, everything required to generate code for each respective code generation framework. And here are the results. As you can see, to compile the same code in SQLite, GlobalISel is 2.7 times faster. You can see from this chart that SelectionDAG has two really long-running phases to generate code, and that's the DAG combiners. SelectionDAG runs the DAG combiner actually multiple times during compilation, and those combiners account for more than half of the overall compile time. On GlobalISel, however, most of the compile time is taken up by one phase, the IR translator. The legalizer takes then the second longest time, and the rest are fairly equal. For this next part, we're going to look at the GlobalISel compilation pipeline, and then more specifically how we've adapted that pipeline to generate optimized code for AArch64. First, let's take a look at a simple add instruction, add I64. The first part is the IR translator, and that simply takes the input LLVM IR instructions and generates an equivalent generic machine instruction. And you can see on the left that we generate an instruction called gadd, and the S64 type is the GlobalISel equivalent of I64. Now, after translation, the one thing we have to do no matter what is we have to run the legalize pass. And the legalizer mutates the instruction if necessary to make it legal. Legal is defined by the target, and really what it means in GlobalISel is that it's a valid selectable instruction. Now, 64-bit adds on AArch64 are legal, we don't need to do anything, and so for this it's simply a NOP. After legalization, the next mandatory pass we have to run is register bank selection. Register banks are again defined by the target, and for AArch64 we have two register banks, an FPR bank for floating point and vector values, and a GPR bank for everything else. An integer add uses the GPR register bank, so that's what we assign here, and we're done. And finally, after register bank selection, we run the actual instruction selector part, and that takes this generic machine instruction and finds an equivalent target instruction to implement that. And since it was legal, this is a very simple selection process. We just select a 64-bit add here. So, where should we place optimizations? Well, here's our pipeline from before, and the first obvious place we could put it is right after translation. And that's what we do. We add the combined pass after translation, but before legalization, and so we call this the pre-legalizer combiner. The purpose of this combiner is to clean up instructions that the IR translator generates, and to simplify things as much as possible before we get to legalization. This allows us to keep the legalizer simpler, and also improves compile time because we don't have to process as much code. In this combine, we also take the opportunity to do things like memcopy inlining. Now, after legalization runs, we have another opportunity to do some optimizations, and we do. We call this one simply the post-legalizer combiner. The purpose of this combiner is to clean up things that the legalizer generated, because the legalizer doesn't really do things like instruction combining. It leaves that to later passes and allows us to have a more modular structure. So, what happens after that? Well, we do regbank selection. However, for the individual targets, there's usually a lot of optimization opportunities still left over. And so usually the selector will also do optimizations. And for AArch64, that's true as well. We implement quite a few manual optimizations at selection time. We do things like optimizing compares and branches, selects, etc. And so the selector is not only an instruction selector, it's also a form of optimization itself.
Now let's talk about how we can lower complex operations. Some operations like gshuffle vector can be complex to optimize and to select. For AArch64, we don't use custom legalization for shuffles, so let's take a closer look at the post-legalizer pipeline. If a shuffle remains intact through the post-legalizer combiner, then the selector is responsible for all remaining optimization and lowering. Now, this is possible, but it adds a lot of complexity to one pass. The selector can't easily create new generic machine instructions after a regbank select, and so we decided to add a custom lowering pass instead. Post-legalizer lowering runs at all optimization levels. It can optimize, but it also contains necessary transforms for selection. We essentially split the selection process over two passes. Let's take a look at an example. In this example, we're going to look at a gshuffle vector with a reverse element mask. In AArch64, this shuffle vector can be represented as a 64-bit rev instruction. We're going to show how we can use post-legalizer lowering to avoid adding unnecessary complexity to the selector. So what do we need to add to post-legalizer lowering? What we're going to do is we're going to create a combine in post-legalizer lowering, which does two things. Firstly, it'll determine if the shuffle vector is an AArch64 rev instruction. And secondly, it'll replace the shuffle vector with something representing that rev if the matching was successful. The interesting part of this is the matching function, since that's where most of the complexity lies. Let's take a closer look at this matchRev function. MatchRev for a 64-bit rev looks something like this. Since we know that this is a 64-bit rev, at the end of this function, the match will be successful, and we will replace our shuffle vector with this AArch64 grev64 instruction. So what is that? grev64 is a target-specific generic instruction. This sounds a little strange to say out loud. The first thing that this does is it gives us a way to record a match prior to selection. So we could theoretically perform combines on things that we know to be rev instructions without having to match a rev multiple times. The second thing it gives is that it allows us to say that the grev instruction is equivalent to the AArch64 rev64 SelectionDAG node. This gives us the ability to pull in the SelectionDAG patterns for AArch64 rev64 and use them to select grev instructions. These patterns range from simple selection to some classes of optimizations, which ought to happen at the point of selection. So let's jump forward a bit and say that we're finished regbank selection, and now we're directly at the point of selection. So at the top, we have our grev64 instruction directly before selection. Okay, so remember that equivalence we created before. Well, we imported a bunch of selection rules. These selection rules tell us how to select grev based off of its inputs and its outputs. In the AArch64 selector, this function called selectImpl will try to use one of those patterns on every instruction before trying to handle it with handwritten C++. In this case, we were able to select based off of one of the rules, and so with 0 lines of code added to the selector, we actually gained selection support for many rev variants. We also gain support for TableGen-defined optimizations involving Rev. In addition, we managed to do so in a way that allows us to record that we found a Rev, opening the door to say, combines on G-Rev instructions. So what's the road ahead? Well, we need to fix our major performance outliers and continue pushing on code size for OS. At this point, this is a long tail where we don't get as many huge wins with a small amount of work. However, we are getting close, and within a few months, we can expect to be on par with SelectionDAG for our key metrics. We also have fallbacks to SelectionDAG to clear. A fallback allows us to use the existing SelectionDAG implementation when GlobalISel doesn't know what to do. Clearing fallbacks is important for having accurate performance results. At this point, we're around 1% on average as a fallback rate. Eventually, GlobalISel should support everything SelectionDAG does without needing to fall back. The most major milestone of GlobalISel is to enable it as the default selector for AArch64. Today, the point where it will be a net win to enable GlobalISel is near on the horizon. SelectionDAG has been around for a long time. It's had significant industry-wide engineering investment into it, but in a relatively short amount of time, we've managed to improve GlobalISel to the point where it's nearly on par with SelectionDAG across key compiler metrics with significantly less effort. Architecturally, GlobalISel is easy to extend and test and improve upon. And so we'd like to push forward with enabling it by default for Darwin once our metric targets are reached. Now, GlobalISel does have a significant investment in it, perhaps not the decade or more of SelectionDAG, but we'd like to thank work from others working on other targets, both downstream and in tree. Occasional contributors for patches and drive-by reviews have been a pleasure to work with, and thank you to other external projects for providing bug reports and helping us drive GlobalISel forward. So now we'd like to open the floor for questions. Thank you.
Thanks, Jessica and Amara, for a great presentation. And let's get started with some of the questions we already have. So the first question is, do you allow the pre-legalizer combiner pass to create illegal instructions?
Yeah, I'll take that one. Yes, we do allow that. One of the advantages of having a pre-legalizer combiner is that you don't necessarily have to care about whether what you're generating is legal or not, because it's going to be legalized later. For the post-legalizer combiner, that's a different question, and there we have to be much more careful that we don't introduce illegal operations, and we have hooks that we can call into to check whether something is going to be legal, and the combines are usually guarded by this check in the post-legalizer combiner.
Okay, thanks. The next question is, what are the most common kinds of inputs that cause the fallbacks?
We used to have a few different variants of fallbacks that accounted for, let's say, 80 or 90% of them, but we fixed those, so now we're basically at the long tail, and these fallbacks are pretty much fairly rare use cases. I think one of the more common fallbacks that we've yet to address is all the different kind of permutations of shuffle vectors. We still have some work to do around canonicalizing some shuffles into forms that we can deal with, but that shouldn't be too much work. And I think the rest of the fallbacks are usually around things which we just haven't implemented legalization for. And so nothing fundamentally too difficult.
Excellent. The next question is, do you find that using GlobalISel reduces the need for machine instruction peephole optimizations that were further reducing compile time?
Good question. Jessica, do you have any thoughts on that?
I don't think that we've actually looked into that, so it's kind of hard to give a concrete, satisfying answer to that question. I imagine that there's probably some peoples that we could do a bit better on, but I think that we need to actually take the time to investigate that to answer the question.
Yeah, I mean, for sure, we do have opportunities within the pipeline to do people-like optimizations. So I think for AArch64 there are things like perhaps optimizations around FMAs and things which we could potentially move into the GlobalISel pipeline. But I think for now we've been taking the approach of don't change what's not broken. So for now we'll leave things as it is. But for sure, if an optimization does make more sense to perform before instruction selection on a generic machine instruction IR, then we definitely look at that.
Okay, thank you. The next question is, to what extent is the improvement in compile time driven by GlobalISel relative lack of optimization? With a whole function view, could some optimizations not be more expensive than in SelectionDAG?
So I think for the first part of that question, I don't think that's really the case, that the lack of optimization contributes to the difference in compile time, because we are fairly close in runtime performance and code size, and for sure that combiner is a very expensive part of the SelectionDAG pipeline. But I think we could implement the majority of the missing optimizations and still remain significantly faster. I don't think that's something that's unrealistic at all. It's a good question because we do expect perhaps some slowdown relative to SelectionDAG as we flesh out the remaining missing features, but I'm expecting them to be increase the GlobalISel part of the pipeline by 10 or 20% in compile time, which would still leave us significantly faster. For the second part, I guess. Could you remind me of the question for the second part?
So the second question, the second part was, could optimization in GlobalISel not be more expensive because they have the whole function view, and we have only a few seconds left? So.
Okay, yeah, sure. Potentially, yes, but we haven't implemented many, cross whole function optimizations yet. So it's not a problem that we've seen so far. Yeah.
Okay, then thanks for taking time to answer the questions, and thank you again.
Okay, thanks.
Thank you.